Good morning, everyone, and welcome to our webinar on composites and metals, exploring complementary printing technologies. My name is Alexander Kreis. I'm a content engineer here at Markforged, and I'm joined by Marco Medecki, our marketing coordinator. On to our agenda for today. I'll first talk a little bit about Markforged, then I'll go into manufacturing ecosystems and what's important to consider in a manufacturing workflow. Then I'll discuss our two complementary 3D printing technologies, our composite systems and our metal systems, and how they can interact in machine shops, in production lines, to enable a wider range of capabilities. Next, I'll go into design in a printing ecosystem, where I'll discuss how you can efficiently use our technologies and our cloud-based platform to get the parts that you need. So a little bit about Markforged. We were founded out of MIT in 2013. We're headquartered in Watertown, Massachusetts, and we have about 140 employees currently. We shipped our first printer, the Mark I, in 2014, and we have about 300% year-over-year growth, achieving profitability in Q1 of 2017. We have employees coming from a diverse range of institutions and industries, including MIT, Tullio, Cisco Meraki, Bell Labs, Sonos, Enernoc, and Olin College. Our products cover the full range of engineering-grade materials, from plastics to composites to metals. We have products that reinforce plastics with continuous strands of composite fibers, and we have a metal printing process that allows you to go from design to your fully completed part very affordably and very efficiently. Markforged customers are global. We've shipped thousands of printers worldwide to over 50 countries, and we offer on-site local support and training in each region through our network of value-added resellers. Our products are trusted by leaders in many industries. Thanks to the unique nature of Markforged parts, we've seen widespread adoption of our technologies in many verticals. So Markforged has become the go-to answer for strong industrial quality parts. And our mission at Markforged is to empower engineers to unlock the next 10x innovations in design and manufacturing, to essentially liberate designers and engineers from decades-old slow processes and enable faster, streamlined manufacturing. So now let's go into the modern manufacturing ecosystem. In a manufacturing ecosystem, nothing is ever focused on one manufacturing solution. One solution isn't enough. Manufacturing is an ecosystem where many technologies work together to produce these parts. So for example, in this image here, we have a connection rod that was originally cast and then post-machined, and we have a 3D printed inspection fixture that is being used to support the part during a QA process. So it's not just about the final part or the final product, it's about how all of these manufacturing systems interact that's important. And high-strength 3D printers can support other manufacturing processes to enable quicker and more streamlined manufacturing. So now let's talk about where 3D printing can fit in manufacturing. Oftentimes, custom low-volume jobs like tooling, fixturing for the production line can restrict machine bandwidth, when your CNC machines can be better utilized making these production parts. So work holding can often take up design and fabrication time that could be better spent elsewhere. So where 3D printing can come in is in assisting these technologies. 3D printing can simplify the manufacturing and assembly process by freeing up a lot of the restricted machining bandwidth. So in this picture here, we are machining a off-the-shelf sprocket to increase the size of the bore in the center. And what we've done is we've printed soft jaws on our composite printers to assist with that operation, where it would be traditionally a little bit harder to fixture. What the soft jaws enable is a much better clamping force on the face and on the teeth of the gear. The soft jaws are highly precise, so in a production run, you can swap out sprockets and machine each one without having to worry about any loss in precision. The main plastic that our composite printers print in is called onyx. It's a chopped carbon fiber nylon blend, and one of the huge benefits of this is that, number one, it's chemically resistant, so Markforged composite parts hold up in manufacturing environments really well because they're not affected by machining fluids. Two, the part is very tough, durable, and wear resistant because of the fiber reinforcement. So this can last thousands of repeated cycles on a manufacturing line with little to no wear. So now let's talk about our two different technologies. We have our composite technology. We can print in continuous strands of composite fibers, as I just discussed, that allow our parts to be very tough, very resilient, and very strong. And we also have our metal printing process where parts get printed in a plastic binder metal powder mixture that gets laid down layer by layer, and once the part is built up, it gets washed and then sintered where the binder melts away and the part solidifies into a solid metal part. Right now we print in 17-4 stainless steel with a few other materials along the way. So with these two printers, you have a wide range of material options that you have access to. On the composite side, we can reinforce with fiberglass, Kevlar, carbon fiber, or a specialty high-strength, high-temperature glass. And on the metal side, we have parts that are roughly equivalent to stock stainless steel. This broad range of material options is very important because it enables broader applications in your manufacturing workflow, can cut costs, and can save time. So on our composite side, you can pick and choose what material properties are necessary. We have carbon fiber, which is very lightweight and stiff, fiberglass, which is very robust and economical, and Kevlar, which is very tough and shock absorbing. And on the metal side, you can achieve the results that you'd expect out of stock 17-4 stainless steel. So this gives you a diverse range of materials to select from. On our composite side, you can have strong but lightweight parts, very tough shock absorbing parts, and non-marring parts because the composites have a plastic matrix material that won't scratch any metals that you're working with. And on the metal side, you get isotropic strength because of our sintering process. You get a high surface hardness, increased wear resistance, and high temperature corrosion resistant properties. So now let's look into how these two technologies can complement each other to support manufacturing. In manufacturing, we're often looking to see how we can make a process more streamlined, cost and time efficient, more scalable, and flexible. And in these spaces, 3D printing can help out a lot because we're able to produce these high-strength parts that are tough enough to survive on a manufacturing floor very cost-effectively and very easily. So we're going to explore 3 different interactions between metal and composite parts on the production line. The first is in processing and inspection of metal 3D printed parts. So our metal parts can be post-processed just like any other metals that you'd find traditionally. You can post-machine them, you can harden them, and you can finish them in a variety of different ways. This part that's here on the right is a needle-bearing housing. We need to make sure that the bore on the inside is very precise so that we can press fit a needle bearing into it. One of the issues that arises is that this part is going to be very complicated to fixture traditionally. So while metal printing can eliminate a lot of the design for machining constraints, because you're designing for an entirely different process, this makes it hard to fixture in your machine when you're going to be boring out that hole. So this is one of the places where composite printing can benefit, where it can be used to create these cost and time effective soft jaws. So we designed and printed a set of composite soft jaws that are conformal to the part that we just designed and allow us to very securely fixture this needle bearing housing so that we can machine out that bore on the inside. And here we're machining this part out with the 3D printed soft jaws and the 3D printed metal part, as you can see right here. So this can apply to a lot of other different post-processing techniques as well. So if you've printed a very organic shape that has holes that need to be tapped, you can print a conformal piece of work holding that will support the part in the orientation that makes it easiest to tap. So for this part here, we have some pretty complicated geometries and features that prevent it from just being able to clamp it to a table and tap it. So we printed a piece of composite work holding that allows us to orient the part in a direction that it can be tapped easily. This type of thinking applies to fixtures for QA and inspection as well. If you've 3D printed a metal part in a low volume end use application and you need to confirm that it meets your quality specifications, then you may need to fixture it for its inspection process to verify that the dimensions are correct. And again, this is where our composite printers can come in because they allow for very sturdy, very reliable, and very precise fixtures. So processing tools is another example of where composite printed parts can come in to help with finishing on metal printed parts. So this ball joint that you see here, this is one of our metal sample parts. We make hundreds of these a month. And what our production team does is they put a little bit of lapping compound on the threads to just help smooth them out a bit. They put it in this tool, this composite tool that they've designed for this part, and they use that tool to essentially just run the threads a little bit and get the lapping compound through each of the grooves so that the threads fit very nicely together between the two pieces. So there we have a finished metal ball joint, and these tools are used on every single ball joint that goes through our production process to ensure that all of the threads are meshing nicely. So inserts for tooling is another thing that we're going to talk about when it comes to metal and composite printing complements. In some cases, you'll want to print in either composites or metals because of a specific material property. You may want to print in one of our fibers because it gets you very durable, very lightweight parts. Or you may want to print in stainless steel because it gives you very hard, very wear-resistant properties. And you can combine these properties where it makes sense on your production line to develop better tools. So in this example here, we have a composite wrench with a metal printed insert that snaps into the end of the wrench that interacts with the part that we're going to be screwing in. So this tool is designed to screw in L-joint anchor bolts. And what's really important here is that the surface that's interacting with the bolt is going to go through a lot of repeated wear where it's pressing up against the bolt surface. And so we can print that insert in metal, localizing where we need that hardness and that wear resistance, and print the rest of the tool in a composite material like fiberglass where strength and stiffness is needed. But what this allows for is to overall maintain the part functionality while vastly decreasing the cost and the weight of the part. The tool ends up being very ergonomic because it stays lightweight and the whole thing doesn't need to be metal, just the insert needs to be metal. So what you can think about when it comes to tooling is where does it make sense to have those metal properties? Where do you need surface hardness? Where do you need wear resistance? And you can adapt the other parts of the tool for composites to generate an overall more ergonomic, lighter weight part and decrease the cost and weight of the tool overall. So now we'll talk about the third metal composite pairing, which is production line interactions. This section is a little bit unique because it's less about creating a specific part. For example, in the processing section I discussed earlier, you're printing a metal part and using composites to post-process it. With tooling, you're creating a tool that has both metal and composite printed parts within it. But here it's more about the ecosystem and the interaction. So different technologies can fill different niches in the production line. As a result, our different printing technologies can support each other and deliver these factory-capable results. So here we have one of our customer examples, Dixon Valve and Coupling, uses metal 3D printed gripper jaws to precisely grip these couplings that they manufacture in their production floor. What you can do in situations like these is again use the composites to print your tooling and your work holding. So a robotic arm comes in and needs to precisely locate and grab these parts to move them between manufacturing processes on the production floor. And we can use composite printers to print a lot of the work holding and alignment tools that will assist in this process. So all of the couplings here are seated within composite printed fixtures. So when the metal printed gripper jaws come down, the robotic arm knows exactly how these parts are oriented due to these composite fixtures. So the coupling can be picked up and placed surely in a different location in a precise orientation. And so interactions like these between metal and composite parts allow for really great applications and great use cases of our two different printing systems and how they interact on the production floor. And all these interactions are made possible by the 3D printing ecosystem that we've developed to help our customers keep track of prints and run and monitor printers. So this makes it very easy to both design and keep track of your parts through the printing process. So let's go a little bit into part design. Because design for 3D printing is much different than other manufacturing methods, there's a lot more you can do in specific areas. So conformal work holding is a great example of that. If you are developing work holding more traditionally, it's hard to create conformal work holding that very securely grips your part while it's being machined, and that's just because of the limitations of other manufacturing processes. So machining soft jaws like this would be very time consuming and very difficult because you have these complex curves on your part. But it's very easy to 3D print soft jaws like this because in 3D printing complexity is essentially free. So conformal work holding ends up being very simple to design and print once you establish a template. So here we developed a template in our CAD software for soft jaws that we know fit on the vise on our milling machine. And once we have this template, it's very easy to modify and very easy to drop in a part and create tooling for that part. What we did with this needle bearing housing is we located the part where we wanted to with respect to the soft jaws, and then we subtracted away the intersecting material between the two parts. And by doing that, it's a very easy and simple design step that essentially automatically creates these conformal soft jaws for this part without much design time. So overall, by printing the soft jaws in composites, you're eliminating a lot of the machining setup, a lot of the manufacturing design that you'd normally have to do on a set of soft jaws, and you are given this very simplified process where you can create a template for soft jaws and easily drop in a part to create work holding for it. So overall, with the two processes, you have a simplified design process where you can design parts exactly how you need them without having to consider many of the designing for machining constraints that you may experience designing something using a milling machine, and you can very easily create the fixtures for that part if you need to post-machine it. Our software platform really enables this simplicity in design where you can upload your files to our software platform, store them in projects based on their application, and whether you have 1 or 100 printers in your organization, you can manage your fleet of printers to keep track of your parts and your material. So our composite printers and our metal printers are all connected to your organization's Markforged software platform. As a result, you can manage projects and you can manage when and where your parts are printing to keep track of the workflow and keep track of the overall system. Because all of these printers are part of a single ecosystem, it's very easy to keep track of and monitor your parts as they're being manufactured. You can check on printer status remotely, receive updates based on how your part is doing, and you can manage projects, printers, and version history within your organization's software platform to ensure that your parts are getting out when you need them. So across our multiple technology platforms, you have an easy way to monitor and control all of these prints to ensure that you're getting out your prints when you want them and how you want them. Thank you everyone for attending the webinar. We're going to open the floor to questions. We may not be able to get to everyone's questions today, but if you have a question that wasn't answered, please feel free to reach out to us via our website where we can help get your questions resolved.